my name is Taylor Cole, and this is my molecular diary number 2. I'm doing it on lidocaine. To review from last video, we talked about the functional groups in lidocaine. I have 3. So my first one over here, I have a tertiary amine. I also have an amide, and I have an aromatic ring over here. We also talked about the hybridization of a couple atoms in lidocaine. The first one we talked about was my nitrogen over here that has an sp3 hybridization. It has 3 bonds right here, different carbons, and then it also has that lone pair, giving it that 4th electron group. You can't see the lone pair because in skeletal structures it doesn't show the lone pair. So it has an sp3 hybridization, giving it an electron arrangement of tetrahedral, but then it has a molecular geometry of trigonal pyramidal because of that lone pair up there. Over here, for this carbon right here, it has an sp2 hybridization. That's because it has 3 electron groups right there. The double bond only counts as 1 electron group, giving it the 3 right there. Has an electron arrangement of trigonal planar, also a molecular geometry of trigonal planar because it has no lone pairs. So that's what we learned in last video. This video we're going to stop talking about the polarity. To figure out my polarity of lidocaine, I decided to use the carbon ratio since my molecule is a little bit bigger than just the simple, tinier compounds and molecules. To start off with my carbon ratio, I decided to count all the carbons in lidocaine, and it's in my formula, so it's 14 carbons. I then had to go through and find only the polar functional groups. So I have 2. 2 out of my 3 functional groups are polar. I have this tertiary amine over here because it has that nitrogen in it. I also have the amide, which is the polar functional group because, again, the oxygen and nitrogen right there. My aromatic ring, however, is nonpolar. That's because it's made of solely carbon molecules with single and double bonds in a ring-like formation, but since it's only made of carbon, that makes it nonpolar. I plugged this into the carbon ratio, and that gave me a 14:2 ratio of my carbons to functional groups, my polar functional groups. Simplified down 7:1, and that's still nonpolar, so I'll go ahead and write that in right here. Okay, so that's there. The next thing we'll talk about is solubility. It is not very soluble in water because it is nonpolar. And water is a polar molecule because like dissolves like, it does not dissolve that well in water. However, it does dissolve better in other solvents like alcohol. And so I looked up on the website and it said that it does have a solubility of 1.75 times 10 to the negative 2 grams per 100 milliliters of water, and that's not very much solubility it has in water. And so it's just because of that nonpolar not dissolving with the polar molecule of water. It does dissolve that little bit because nonpolar molecules still do dissolve in water even though it is the nonpolar and polar again, and that's just because all solvents do. And then every time that it dissolves more, they just exchange places in the solvent. And so that's how it does that. The next thing we'll talk about is the forces. So it is nonpolar, so it only has dispersion forces available to use. Dispersion forces are the temporary uneven distribution of electrons within a molecule, giving it temporary dipoles. So it only has dispersion forces all among it, and that's the weakest forces of all the different intermolecular forces they have available to it. And that's just because it is nonpolar, like I said. And because of this, it gives them a low melting and boiling point is what is expected for them to have. My website said that lidocaine has a 68.5 degree Celsius melting point and 181 degree Celsius boiling point. And that's not very high for something to melt and boil lidocaine, and that's again expected because of the dispersion forces within it. So going back, we learned about the polarity, and it is nonpolar. And we also did learn about that it is not soluble in water, so I'll go ahead and write that in as well. Non-soluble in H2O. And the last thing that we learned, it was that it has dispersion forces. and that gave it the low melting point and boiling point. And that's it for my molecular diary number 2. Thank you.